Good afternoon, everyone. Thanks for joining this machine learning session, and I'm honored to be the first presenter for you. I'm Jianpeng. I'm PhD student, fourth year PhD student in ETH Zurich, and Zhang, my colleague here, he will join us for the Q&A sessions. So today I'm going to present our study on energy-aware design predicting building performance from layout graphs. So for your understanding, I try to summarize three keywords. The first, building performance prediction, and second keyword, the architecture layout, and the third one, the graphs. So let's start. Let's look a little bit around about the research background. So everyone knows the building industry is responsible for 35% of global energy consumption. That is also to say that this industry has much potential to reduce energy consumptions. And investment in energy efficient design in building is increasing, but still lags much behind compared with other building construction investment. So it's crucial to conduct the energy performance analysis during the early design stage. Existing studies have shown that the decision made at the early design stage can save up to 30 to 40% of energy usage with no added cost. Then let's look at some challenges and motivations for this study. So generative design has been a widely used tool to achieve customization and efficiency in building designs. So however, generative design for the floor plan, specifically for floor plan, seldom incorporates energy performance. So you can generate like thousands of floor layout, but without understanding how the energy performance go with each design. So in practice, like what we usually do is we select few preferred schematic design from the pool of the designs and go through with the traditional energy simulation tools. And many parameters are usually uncertain but required at this early design stage. So overall, the simulation for the building energy performance estimation is time intensive and too slow for the real-time feedback. There's an alternative approach to use data-driven approach. So the data-driven approach relies on the machine learning algorithms, and the previous study applied, for example, the decision tree, neural network, random forest, and support vector machines on the energy performance prediction. They have shown that this strategy has efficiency to require less information but generates the result in shorter time. And however, when the exterior factors such as the site and the weather condition are fixed, the spatial layout as the most important design characteristics during the early design stage has not been considered or well structured in the prediction task. And there are two motivations for our research. The first one, the floor plan design or floor plan generative design use graph-based model, usually graph convolutional networks. It's intuitive to use the same data structure, the graph structure, for the building energy performance analysis. And second motivation is the spatial layout of the design has been proved to be important design variables for building energy performance. So here, the spatial layout does not only refers to the room or space types, but also you can infer from the expected temperature during the operational stage, given a specific room type or space type. And the spatial layout also includes the room-to-room connections. For example, you can have the door connections between rooms, you can have the partition wall connections. For the open space, you might need the open connections. So given that, we propose a methodology. We use the GNN-based approach. The GNN stands for the graph neural networks to predict the energy performance using the layout graphs. The methodology can be applied to other engineering domains, for example, the construction cost and time estimation. And in general, this methodology contains two parts. The first part is a prediction model, and the second part is an explanation model. So for a given objective function, the GNN models, graph neural networks, are used to predict the performance. And the graph neural network models can be built just by a simple model can be built just by the multiple graph convolutional layers and the fully connected layers. And once the result is obtained, we further use another graph neural networks, and plus specific techniques. We have a masked mechanism to conduct a sensitivity analysis. So in the end, the output is we can find the dominant element. So here the dominant element refers to the element that has more effect or more sensitive to the selected objectives. So in the output, it shows you the important index for each node and important index for each edge. Using the graph model, like we can consider the interaction between the studied variables. So for example, in the construction scheduling task, we can find the most important element or activities, which might need a specific buffer for that, or or for this study, we can find, for example, the room which consumes more energies. And let's look at the specific research questions. So for this study, we are focusing on the first prediction model. So we are supposed to use the spatial layout to predict the building energy performance. So specifically for the heating and the cooling node here. And this can be divided into 3 research questions. So first, does the spatial layout influence the building energy performance? Although this has been proved by previous studies, we are going to test this again from a different angle. And second, how does the spatial layout can be modeled by graph? And third, given there are so many GNN models, which one do we use for our task? And do we have some criteria to select among them? So let's look at the workflows. The workflow consists of 3 major steps. So first, we are going to generate thousands of floor layouts, and then we are going to use a simulation tool to calculate the energy consumptions, the heating and cooling node for each design in our dataset. And second, we are going to represent the architecture layout in the dataset as graphs. So in detail, we represent each room and space as nodes. The property of the room and space, like the functionalities of the rooms, the area, we represent it as node attribute. And for the edge, we used adjacency matrix to represent the element-to-element connections. So here we didn't consider the connection types. So what we just mentioned before, whether they are door connection or they are partition wall connections. That's what we want to do in the future step. And finally, we use the prepared dataset to test the GNN models for the building performance prediction. And let's look at the dataset generation. So the energy simulation, we used a tool called the Radiance and the Ladybugs in the Grasshopper, and we fixed the site and the weather parameters, and also the structure types, and for this study. And to prove that the room layouts does influence the energy consumption, we did what we call the room swapping test. So for a given design, we randomly swap 2 rooms, but fix the number of rooms and the types of the rooms, and then calculate the energy consumption for each design. We did this 100 times on different floor plans, and find that the floor layouts do influence the energy performance. In the end, we generate over 3,000 floor plans, and you can see the floor layouts. We have more freedom on that, and a wider range of energy consumption. Then let's talk about how do we select the available GNN models. So we take a literature review on the existing works on the GNN models, and we also consider the characteristics of the architecture design we propose like there are 3 criteria we might consider when selecting for the model selection. So the first, whether the age property are considered in the model. So here the age property refers to the types of spatial relationship. So as I mentioned before, this can different connection types. And the vanilla graph convolutional networks, the GCN and graph search, has been studied that they are not supported the age. So age properties are not used for the message passing process. So they are not perfectly suitable for these scenarios. And the second scenario is whether the architecture floor plan, the layout, has a high degree of spatial connectivity or no degree of spatial connectivity. From a mathematical point of view, this refers to the adjacency matrix is a sparse matrix or dense matrix. And the previous studies shown that the gated GCN are not suitable for the dense graph. And the last criteria is the number of space or the number of nodes in the graph. Because most of the GNN studies has targeted on the small size graphs, like the molecule graphs. They're not only like the graph search and the gated GCN, they did some research on the large size graphs. So for this study, since our floor layout is quite simple and with no age features, all above models are suitable for our study. And let's look at some implementation and result. So we use our prepared data set, and we split it into 80% to 20% for the training and testing set. We try variant configurations for the hidden layer numbers and the different batch size scale. We evaluate the performance of all those models from using the mean absolute error and the mean absolute percentage errors. And you can see from the table, like all the tested models have a stable and decent performance of our defined energy prediction task. And around 85% to 90% accuracy is achieved. And limitations and our future works. One of the major limitations is the variable now influencing the energy performance are not fully taken into account and taken into the prediction models, like the age properties we just mentioned. So this gave us like 3 research directions for the future works. We are going to encode more architectural features, such as the room locations, space relational types, and the materials for the space in our graph models. And secondly, we are going to, once we have more features included, we are going to compare the performance of GNN models using the 3 criteria we just proposed. And finally, we are going to step forward to the second explanation model, try to investigate whether the GNN can be used to find the dominant elements for given objective functions. So a preliminary result we have found, you can see from the left side, if this graph represents a floor plan, the size of the node represents the important index given the energy consumption objectives. So the bigger size of the node, which means this the energy consumption for this node, for this space, is more sensitive, and this tool can be used for the designers to locate the key elements and use that to support the next optimization. So, for example, for the construction task and construction process, the managers can use that to locate the critical elements and set the buffer for that. So you can find this methodology can be applied to different domains. Thanks for your attention, and I'm looking forward to your questions.